So what I show you might encourage some questions. So this is part 2 of 3 about things related to symbolic calculus in Sage. So the main topics we'll talk about are finding roots both symbolically and numerically. The homework doesn't have anything about finding symbolic roots, but it's of interest to know about how to do that, of course. And then numerical, you've probably tried that already when you looked at your homework. Then I'll also talk about how to numerically approximate a symbolic expression. So if you have something like square root of 2 plus e, or some big thing that pops out of some calculation, how can you get a floating point result, and how can you control the number of digits, and also just understand what the heck it's doing when it gives you a result. And then I'll tell you a bunch more about 2D plotting and visualization that is separate from plotting functions. So for creating visualizations, things like drawing a bunch of points, drawing a line through points, drawing text, etc. And I don't think I'll have anything about 3D plots. Okay, so let's start with finding roots symbolically. So there's a command in Sage called solve, and you can give it a symbolic equation. This is something that I've never talked about before, but here's a really simple one. If you have a symbolic variable x, and you say something like x squared plus 3 equals 5 with a double equal sign, look what happens. It doesn't say true or false. It just gives you back x squared plus 3 equals 5. It's like a formal symbolic equality. And there's a solve command that takes as input such things. And you can also manipulate such an object. Like if we let EQN equal this equation, you can do like show EQN. And there's various methods that you can do, like EQN dot add to both sides. So let's add, I don't know, minus 3 to both sides. And you'll get back an equation obtained by adding to both sides. Okay? So you can formally manipulate symbolic equalities like that. If you want to know whether or not one is true or false, so if, an example of how this might come up, e equals pi. So that's just a symbolic inequality. You can do bool of it, or symbolic equality actually, and it will tell you false. By the way bool works on a symbolic equality is it'll say true if it can prove that the two things are equal, false if it can't. So watch out for that. It's not going to, sometimes there are expressions for which it's extremely difficult or impossible to tell whether they're equal, and so it can't tell you that. So if I did pi equals pi, then it should say true. Okay. So back to solve. So in this example, I'm just giving a polynomial, but sometimes solve will work even if the input isn't a polynomial. And I'll show you some examples in a moment. Notice that this is a cubic rather than a quadratic. So instead of solving using the quadratic formula, it's using a more complicated formula. You can even try a degree 4 polynomial. This will be a big mess. Notice it's pretty hard to look at the above. But if I'll do show the result of the above solve. It gives you back a list of symbolic equations. And here's the solution in radicals of that degree 4 polynomial. There's a general formula for solving in terms of radicals any polynomial of degree up to 4, but there isn't one for degree 5. Sometimes you can solve a degree 5 polynomial, but it's a theorem of Galois that there's no possible way to give a formula similar to the quadratic formula, which solves polynomials of degree 5 or bigger. And him proving that was the birth of group theory and modern abstract algebra. Here's an example of a symbolic equation, square root of x equals 2. And so it doesn't involve just polynomials, since square root of x is not a polynomial, and it finds a solution, as you can see. You can also try to do things like solve, I don't know, sine of x equals 0. And this will show you some of these subtleties, because as you know, there are infinitely many solutions to this, but it's not going to give you infinitely many. It just gives you one. So watch out. For things like polynomials, it does give you all of the solutions. Here's a good example that might come up if you're doing sort of, I don't know, financial type stuff where you have an biology where you have some exponential growth type thing. So instead of having to fudge around with logarithms, you can just say solve. And this, again, on line 55, doesn't involve a polynomial. It involves e to some power equals something else. This is the sort of thing that you know from pre-calculus or high school or whatever, that you can solve by taking logarithms of both sides and then playing around. But it's all automated in here. And as you can see, when you solve, it gives you back a nice answer. Well, I mean, it is what it is. There are a couple of solutions. 2 of them are complex and 1 of them is real. So you notice this third solution is 1/3 log of 5, but there's also 2 complex solutions. There's an option you can pass to the solve command. If you're going to seriously use the solve command, I recommend doing solve question mark and looking at documentation. There's a solution dict option you can pass in, which makes it a little easier to deal with the potential of multiple solutions and how you can get access to them without having to say copy and paste, which is a very bad idea. There's other things like solve can solve a system of polynomial equations. It's not just for a single equation, or even just a system of equations in general. It will attempt to do so. Let me just show you a system of polynomial equations. So I think here we can ask it to solve for x and y. And so it introduces a new parameter which it calls R1, and then it gives us that 0, 0 is the solution, and then also any point where the x and y coordinate are both equal to this parameter R1. So look, I mean, it's true. If x and y are the same, then both of those are equal to 0. Oh, sorry, one thing here is I didn't explicitly give equals a double equals, and so it just assumes that the expressions without a doubles equals are being set to 0, because that's kind of the default. It might be better to write double equals and double equals. It's equivalent to what I just wrote. And you can make it more complicated. Let's put a +5 there. Now it has to be something different. Let's see what happens. So now it solves, and it finds numerically a couple of solutions. Okay? Just found a couple of solutions. By the way, to peek ahead a little bit, there's an implicit plot function called implicit plot, and you can give it an equation, and it will plot the real solutions. And you have to give it a little box where it's supposed to plot the real solutions. So I'll just go from -3 to 3 and -3 to 3. I don't know what it looks like, but see, what it just did was it evaluated x cubed minus y cubed minus 5 on a grid over the whole thing, and then it drew a curve that nicely goes through the points where that thing was very close to 0. And I think we can do something very similar for, well, I mean, you could see x squared equals y squared. Where is x squared equal to y squared? That's where x and y are equal to each other, or the negative. X equals plus or minus y. And so that would be the line y equals x, and then there's a line the other way. And these solutions should correspond to the intersection of those two. I should be able to do actually this, and then make an implicit plot for the other one. I don't know whether you can add implicit plots to each other, but we'll soon find out and see what happens. Oops. You have to show it. Okay, so look, maybe I can do color equals red, so you can see which one's which. So the red lines, those are the solutions to x squared equals y squared, plotted implicitly. And the blue, you can only see one intersection here, but there are other intersections, like I guess at this point right here, that's the one right there. There are other intersection points that Solve found, but maybe they're all complex. I'm just looking through them. They look like they're all, yeah, there aren't any other real solutions. So the only solution is right there. And so this must get really close, but never hit. Okay, so this is the sort of thing that should, remind you of calculus classes and the sorts of things that come up. Given any equation, you can plot its solutions in the plane. And there is something similar in three-dimensional space as well. Implicit plot 3D will give you all the solutions to an equation involving 3 variables in three-dimensional space. And that's useful for understanding solve. If you're ever going to use solving algebraically or numerically, it's, I mean, again, as you should have got a sense for in previous math classes, a good idea to try to draw a plot so you can see what the heck is going on visually. Like here, if you see this picture, and I just made these equations up at random, I didn't do this ahead of time, but looking at the picture, it's reasonable that there should be one real solution. My mouse is sitting on it. And it kind of looks at least reasonable that maybe in the limit this is asymptotic, but it doesn't quite hit. And that's consistent with what you actually saw out of the solve command. You should be really happy that implicit plot exists. I remember that for many, many years we didn't have an implicit plot in Sage. It's a tricky thing to do, but then some guy named Carl Whitty was like, why don't we just use the contour plot function, and then there's some funny options you can pass into it to trick it into giving you an implicit plot. So that's how implicit plot is implemented under the hood. It really uses contour plot with certain options. And it looks pretty good, actually. That's just an example of one of the solutions above. Okay, so there you are. And then numerical, this is something that you've already seen. Here's an example. F of x is a function, and I plot it to get a sense of what's going on. And then down here, I'm going to use find root. So you did this sort of thing already. With find root, you give it an interval, and it gives you back at most one solution or an error. So if you give it an interval where there isn't a solution, you shouldn't expect it to give you one. That would be weird. Although somebody did report to me that they had an example where, actually at lunch yesterday. Okay, so that's what it should do if there's no zero. However, find root, it's just, it takes this function f, it forgets about its symbolic form. It doesn't use solve symbolically at all. It just takes it and views it as something, as a black box that takes as input a floating point number and gives you back a floating point number. And then it just runs some generic solving, numerical solving algorithm, maybe Newton iteration or something like that. You have to look at the docs to see what it currently does. Due to round-off error, depending on what your function is, if your function's really weird, it could be that it'll think that there's a zero even though there isn't one. Maybe there's just something that's really close to zero. So you really always have to use your brain in conjunction with just calling a command like find root. There are, there's a whole department called Applied Math. They teach lots of numerical analysis classes, etc. And there's a whole bunch of really exciting and funny things that happen when you work with floating point numbers. A basic thing about floating point numbers is addition is not associative, right? So in math, in pure math, like we all know about, you do a plus b plus c, and you get the same thing as a plus b plus c. Like it doesn't matter in which way you add them. You can do a plus b first and then add c, or you can do a and then add b plus c. With floating point numbers, like decimals to some fixed precision, you can get a different answer by adding the first two and then the second two. So you have to watch out. The order in which you add matters. There's a quote which is that working with floating point numbers is like picking up and carrying around piles of sand. Every single time you do it, a little bit of sand gets lost. It's like every time you add or multiply two floating point numbers, you should expect maybe there's a little bit that just gets lost. And by cleverly setting things up, which will accidentally happen to you in practice, you can make it so like you add two floating point numbers and get something that's, it's basically like 0.000000, and then there's a bunch of stuff here. And then you add to that something that's like 5. And then when you add those two together, you lose this stuff over here. And then you subtract off 5, and now suddenly you just have completely nothing. So basically you just lost everything, but you'll get an answer, an hour later that looks like a solid answer, but it's complete nonsense. So you have to watch out when working with floating point numbers. This isn't a course in numerical analysis, and I'm not going to go into great depth about that, but I just want you to know that find root, you really want to look at a plot and try to understand what's going on, do something symbolically if possible, etc. And on that topic, Sage does have very powerful support for interval arithmetic. So instead of adding together and multiplying and using special functions involving floating point numbers, you can take little intervals and add and multiply those. And every time you lose a little precision, you make the interval a little bigger. And what you're representing is arithmetic with intervals rather than numbers, so you're just in a sense, you're keeping track of the exact error of your calculation as you go. So Sage can do that, but only if you explicitly tell it to do so. I'll show an example in a minute. But it is well supported and very efficient in Sage. Okay, so I'll do that actually in just a second, but first let me get a number. I just made up some, well, actually I copied and pasted something from above. It's just a big symbolic expression involving radicals, logarithms, and a complex number thrown in there. And if you look at it, it looks like that. You might wonder, what the heck is that number? You just want a floating point number that you can think about. So there's a command, numerical approx, which gives you back a numerical approximation for some big symbolic expression that's constant. Okay, it won't work if you try to pass it in x, because x is an indeterminate. But if you just pass in something that's actually constant, it'll work. But warning, the way that numerical approx works, so that expression, that big log thing, think of it like a tree. It's like an evaluation tree, and the leaves of the tree are these numbers like 2, 5, 3, 3, etc. They're the actual numbers, and I. And then what you do is you do various multiplies, you apply functions like square root, you raise to powers, you apply functions like log to those numbers, and that gives you this. So you can think of this as like a tree. The way numerical approx works, it takes the leaves of the tree and replaces them all with floating point numbers by default to double precision, and then it just evaluates everything up the tree. So you can do a numerical approx, and it can give you back a nice floating point number such that none of the digits are correct. Why? Because there might be a whole bunch of rounding errors as you go up. If it's a really complicated expression and it involves adding big numbers to small numbers and all kinds of crazy stuff happens as you go up the tree, you may get something where it just ends up giving you something that's complete nonsense. So you really, yes?
So I think whenever you show these...
Do you want to see? Yeah, go on.
Whenever you show these expressions, it's always, I think you're probably like omitting like parentheses and stuff, like where
no,
necessary.
There are no, there's an order of operations convention. Right. So multiplication, exponentiation has the highest precedence, then multiplication, division have equal precedence, and addition has lower precedence. So it's all well defined. So there's implicitly, you could view it as having parentheses that match the precedence rules.
Right.
Yep.
But I'm saying, like, is there a way to force, like, we're talking about associativity, for example, is there a way to force A plus B then C versus A plus B plus C? Because, I mean, if
yeah, that's a good question. I don't know the answer, actually. Even having spent a lot of time in the guts of the symbolic representation and implementing this, I don't know the answer to that question. I would say no. There's no way to force that. The question would be, what does it actually do? There's definitely no way to force it to do one or the other. By the way, I mean, let's just come up with a stupid example that illustrates, instead of being all abstract, let's just come up with a stupid example that illustrates what I'm talking about. So 1 over 10 to the 100, right? That's 0.00000 whatever. Now I'm going to add to that pi, and then I'm going to see. So now I have pi plus that, and now I'm going to, I don't know, subtract 1 over 10 to the 100. What am I doing? Maybe subtract 2 over 10 to the 100. It'll simplify it first symbolically, though, so I have to be careful. Oh, I know. I'll do it with pi. So pi over 10 to the 100 plus pi minus e times 10 to the 100. There's just like a very wide range of values represented here. Okay, I'm just making up something funny, but let's see what it looks like. So it's hard to look at. Numerical approx of f, and it just says it's 1. So does that make any sense? So tiny number plus pi minus c. Oh yeah, 1 and then, sorry, 1 with 100 zeros, or 200 zeros after it. Actually, I want to, crop. Something a little simpler. Okay, big, tiny number plus big number plus maybe another tiny number. So the thing is, it simplifies it already, so you have to kind of, we would need something that evaluates to pi, but it doesn't simplify it immediately until you plug something in. Maybe like arc sine of okay, so I'm not coming up with something really good off the top of my head. But basically it's just, if you have something big, small, you just kind of add them together, then you can have cancellation. All right, I'll come up with something next time. Let me tell you more about, so I told you what numerical approx does. It just evaluates at the bottom and works its way up. You can control the precision of the inputs at the bottom. So if you say prec equals 200, it will start with all of the leaves in the tree being numbers with 200 bits of precision. So numbers internally are represented using zeros and ones, and that's the number of bits of precision. Alternatively, you could say start with numbers with 20 digits of precision, and then evaluate everything up. And it'll give you this. So you have some control that way. But again, just to emphasize, it's possible that you could get complete nonsense in the end. However, if you use interval arithmetic, so you make a complex interval field, as it's called, then what will happen is it will evaluate all the leave nodes. It'll substitute in for them little intervals. It'll do all the arithmetic to get your expression, and it will track all the errors. And what you'll get is something that prints out. It looks like a floating point number, but it has this funny question mark at the end. Let me do it to lower precision. And what this means is that every digit is definitely correct, except possibly the last one. And the speed overhead in doing things this way is about a factor of 4, usually. So it's a little bit slower, but it might be fine for what you're doing. So if you suspect rounding errors in something, then there are techniques in Sage involving intervals to address them very easily. By the way, there's an abbreviation for numerical approx, which is just capital N. They're exactly the same thing. If you've ever used Mathematica, you might recognize that in Mathematica, a command to do the same thing is also called capital N. Moreover, there's a method on any symbolic expression called capital N that does the same thing. You can call it as a method instead of writing it out. You can even use lowercase n, or you can write out numerical approx like this, alpha.numerical approx. Oops, there's a lot of, oh, what, am I wrong? Apparently, oops, if that's even right. I didn't see it in the tab completion. Oh, there it is, okay, good. So, okay, so that's numerical approximation. Now let me show you a little bit more about 2D plots. So you can do a lot of other things besides plotting a function. Like you can plot a point, you can plot a cluster, a whole bunch of points, you can plot text, and the text plotting is very flexible. You can adjust the angle of the text, how it's centered relative to other things, what the color of the text is. You can put arbitrary LaTeX formulas in your text, and it all gets typeset really nicely. You can put the text wherever you want. You could draw a line that goes through a bunch of points. It's obviously not a straight line, it's really a sequence of line segments. And that can be really, really useful for, I use that probably more than just normal plotting. You can draw polygons, ellipses, implicit plots I just showed you, contour plots, vector fields, etc. So let me just show you some things with the first of these. Here's a point. So right there. You can control the size of the point using the mysterious point size parameter and the color of the point. And so it's the point at position 1, 2. It has size 150, and its color is red. Yes?
How much does the order of like parameters to like these plotting functions matter?
any of the named ones where you explicitly say point size equals or color equals or anything like that, so these are explicitly named arguments, you can put them in absolutely any order you want. The positional arguments where you don't explicitly say something equals something else, the order is critical. It has to be the way it's given. Okay? And that's just a general statement about Python not plotting. Okay, there's a whole bunch. If you do point, and hit the tab key like I just did, then some help will pop up. Or maybe I have to do point question mark. Oh, there it is. And you can see that there's, there's a bunch of generic options. And I guess you have to do point 2D to see the documentation. There's a point 3D. If I were to do 1, 2, 3 right here, instead of getting a point in 2D, I get a point in 3D. It just automatically kind of switches from 2D to 3D when you give a point that's only defined in 3D. If you want to be explicit and say it's a 2D point, you can do this. And now it'll definitely be a 2D point or an error. And then when you do help, you'll get the documentation. And there's one positional argument, the very first one, which is either a single point or a list of points. And then there's a whole bunch of other options that you can give. Like, instead of the points being round, you can make them little, like, X's, kind of like in MATLAB or something. That's what this marker stuff is about. Oh, and the size is apparently defined below. Okay, here's an example where we take and compute 100 random points and then plot them. And notice the input to point, we're just giving it a list of pairs computed at random. Here's an example involving text, moving on. And I've combined it with some, a point, but the command is text. You give as input, the first thing is a string, and you can include LaTeX in that string, at least LaTeX formulas in $signs. And you will definitely want to do that if you're annotating some mathematical diagrams. There's a key thing here, though, which I think I've never mentioned in this class, which is really important and will totally trip you up, which is this little R right here. It means it's a raw string. So in Python, there are a whole bunch of escape codes. For example, if you do print that \n that, notice there's a little \n right in the middle. What's it going to do? The \n gets replaced by a new line, correct? See? And there's a bunch of little things like that. A whole bunch of there's like 10 or some things of the form \something, and they get replaced by a special character. And that could be kind of annoying because guess what LaTeX does? It has tons of commands that start with a \. And you'll try to do something like this, which involves a little bit of LaTeX, and like maybe \pi works because maybe just coincidentally Python doesn't have a \p thing, but then something else doesn't work, and you'll just be like really confused. Fortunately, in Python, if you put an R at the beginning of the string, then it doesn't do anything with the \. It just leaves them as \. Okay, so what will I see if I put an R right here? And then evaluate. Boom, I'll see a \n right in line. Okay, so that's what the R is. And R stands for raw. The other option is you can put 2 backslashes. One of the escape things that you can do in Python is a \. So \\/ means / without the raw, like this. And you'll get a \ as, wait, what? Okay, there, because I didn't undo. So see how there's a \ in line. So that's kind of annoying though. If you try to take a bunch of LaTeX formulas and double all your \, it will soon start getting very confusing. Especially because \/ is a useful thing in LaTeX. That means new line in LaTeX. So then you end up with like 4 \ in a row. So I strongly recommend using R whenever you're giving some sort of formula or something that involves LaTeX. Okay? So just remember that one thing. It'll save you a lot of frustration. This is a useful thing to know just in general when using matplotlib or Python or Sage for plotting. And here's what the plot looks like. This is really nice because it's kind of gray. Notice it's somewhat transparent. That's what the alpha thing does, so you can make your text kind of transparent. This is a nice vector graphic, so you can include it in a paper or something. The rotation thing lets you rotate your text at an arbitrary angle. You can set the color, the weight of the font, that's why it's a little bit bold, the size of the font, etc. And you can stick the text wherever you want. It's centered at 1, 2, but you can also say that the point where you put it is the bottom of the text or the top of the text. Okay? And you can add lots of text to a figure with plus. So this lets you programmatically generate nice vector graphic type stuff. It's like you can write a little program that generates the sort of thing that you might make using Adobe Illustrator or some program like that. By the way, if you go by my office ever, I have a big poster on my wall, and it has a comic on it that looks a lot like an XKCD comic, but the entire thing was drawn just by using plots like this and text in line. I already showed. This is the line command. You just give a bunch of points, and it draws a line that goes through them. And if you want to put like little dots at each of the points that it's going through, you can say make the line, and then make points at those points, with a big size and a color, and you'll see that the line goes through those points. And finally, the very last thing, this is an example of an implicit plot. I showed you some above, but this one looks kind of cool because it's really sort of complicated to make. And it's not just an algebraic function. It's a function involving cosines and exponentials and stuff. Okay, so we only have 5 minutes left, but I encourage you to try to do something towards your homework, and maybe you'll have time to ask me one question. So, but actually, before we break up, okay, questions that you want to ask in general. You had your hand up first.
A personal question.
Okay. Does anybody have a non-personal question or a less personal question? I can pull up your worksheet, by the way. You?
Yeah, mine is about the homework.
Yeah.
Problem 6. I was just trying to figure out how to, because you have the Taylor series and you have just the normal function.
Not solutions. Okay, I'll open it. So problem 6. And it's taking too long. Okay. Okay, so what's the question?
I just wondering, how do you plot them on the same graph? Because I'm trying to set them up together.
Yes. So given any two plots at all ever in Sage, you just use plus, and it superimposes them in the same graph. Okay?
So I've tried that.
Uh-oh.
Maybe I'll try it.
Okay. Does anybody else have a general question? Yes?
For number 10, what is a torus?
What is a what? A torus? Oh, a donut. A torus, in layman's terms, is a donut. So it's like a donut. You take a circle and you rotate it around another circle, and you get a parametric. You get a surface. So, yes.
For problem 3, part 2, what are we integrating in terms of? I guess I'm unclear about that.
Do you want to say something about that, John? It's your problem.
You're integrating in terms of dt. So you're integrating if you use a dummy variable f of t, you're integrating f of t from negative infinity to x.
Okay, because.
And infinity is OO in Sage.
Oh, okay.
Was that the question, really?
Also, yeah.
Because it's a OO. It looks like an infinity. So that might be helpful. I guess that's plus infinity, so watch out. Minus OO. Give you minus infinity. Okay, any other general questions? Okay, John and I will walk around and answer more questions. I'll stop the screencast.